Okay, welcome back. I guess you had a break last week. You saw the email from Ron. Glad that you guys are making good progress. Okay, let's get started then. Are there any questions? Doing well with the project? All right. So we are looking at methods for solving initial value problems. So we spent nearly 2 lectures on that. Multi-step method, single-step method, stabilities, embedded forms, implicit versus explicit. So you should have some awareness of how these algorithms are developed, what kind of ideas are used, and how we can apply. So that's what we are looking at now, how we can apply those class of initial value problem methods to solve boundary value problems. So something called the shooting method. Okay, so we saw a couple of simple examples in the last lecture, and I said let's look at a more complicated example where we have 2 coupled nonlinear second order equations. So the first equation is given here, and f1 is a nonlinear function of u1 and u2. So u1 and u2 are the 2 unknowns, and we have 2 equations. They're both second order. But the boundary conditions are given such that u1 prime at the left boundary and u1 prime at the right boundary are given values. So alpha is a given value, 0 is 0, of course. Okay. And similarly for the second equation, you have u2 prime at 0 and u2 prime at 1 are given values. So there are 4 conditions that we need because we have 2 second order equations. Each one needs 2 conditions. And so the problem is well posed. And here L is a constant, D1, D2 are constants, and F1 and F2 are nonlinear functions, but known functions. Okay, so it could be e to the power u1 times u2 or something like that. Typically these reactions come from diffusion reaction problems, where u1 could be a composition and u2 could be a temperature, non-isothermal reaction. Okay, so that's the problem. So how would you solve it using finite difference method? You should be able to know. All you need to do is just replace this term with the central difference approximation. Okay, and you get a set of algebraic equations. You set a node between 0 and 1, a number of nodes, and that gives you the discretization. So in the boundary value problems, the idea is to convert them into a system of algebraic equations. Of course, it's nonlinear, and you use Newton method and all the tools that are available from that, the continuation, in terms of the parameters. The parameters here are L and D1 and D2. Okay. If you are going to use the shooting method to solve this problem, now the first question is, why would I want to use the shooting method, which we talked about in the last class? The central difference approximation gives you only of order h squared, delta x squared accuracy, whereas we have Rangakada method of order 4, for example. So, and the algorithms are much more developed for initial value problems in terms of the automatic step size control and stiff differential equations. If we have a sharp change in u1 or u2 in the domain 0 to 1, we can march through them much more effectively. Whereas with finite difference method, you don't know a priori where the sharp change is. But there are similar developments that have taken place. OMSOL has them, so-called adaptive mesh, that will once gets a solution, it uses that to estimate where the gradients are sharp and puts more grid points there automatically for you. But the shooting method, how would we implement that? I thought this was a very nice development, and so I wanted to talk about that. Okay. So if that is the problem that is given to you, just think about how you would apply shooting method to the problem. The shorting method requires you to convert a boundary value problem into an initial value problem so that you can use an initial value algorithm. Okay, that would mean in this particular case that I need to come up with two more conditions, okay, at the left boundary. So at the left boundary currently I have two conditions, so I need to guess two more conditions. For example, U1 and U2. I'm given U1 prime and U2 prime. So if I can guess U1 and U2, then I will have four conditions on the left boundary. I can convert these two equations into a set of four first order equations, and then I have the four functions. I can write that in MATLAB and then put the four initial conditions and shoot. But what would I expect? When I shoot and when I get a solution, I will get a solution for U1 and U2. Okay, so U1 versus X. So U1 prime is already given, that is 0. But U1 I'm going to make an assumption. So solution is going to start off horizontally and then it may go do whatever you want, but I mean whatever it wants according to the equation. And when X equal to 1, I need to take that derivative and check whether that derivative is equal to alpha. Okay, so I need to check this at the other boundary. Do you understand that? Conceptually, that's what we need to do. We need to come up with two guesses. I've just shown you one, so there will be another one for U2, for example. I make a guess for U2, but U2 prime is given, so using that I integrate, and on the other side I need to check whether the slope is equal to beta. If I did, then I have made the right guess. So what I need to do is develop a systematic procedure where I can change my guesses U1 and U2 so that I will reach my target. Okay, so we are going to introduce the idea of residuals and basically satisfying the residual equal to 0, driving the residual equal to 0. Any questions on that? So that's the problem formulation. Okay, so you have two equations. You should be able to generalize this to any number of equations. The idea is the same. Okay, and the shooting method requires you to come up with some guesses on one of the ends, either one of the ends. In this particular case, it doesn't make sense to, there is no advantage to be gained by guessing either on the left or on the right hand side. Suppose I had a problem where I had given three conditions on the left side, only one on the right side. Okay, then where would you guess? On the left, because you have already three conditions, you need to guess only one, and you can verify that one against the right hand side. Okay, but in this case there is no advantage, so we can pick the left hand side. And so I start the problem by saying that the guesses are going to be called eta 1 and eta 2. Okay, the guess for U1 on the left boundary, U1 0 on the left boundary is eta 1, and U2 0 on the left boundary is eta 2. So I create a vector eta which contains two numbers. These are the guesses on the left side, eta 1 and eta 2. Now I need to develop a systematic procedure for developing better and better guesses for eta 1 and eta 2. So I'm going to use Newton method for that. Okay, so using those guesses then, using eta 1 and eta 2 at these points, okay, I'm going to integrate from x equals 0 to 1 and check the residual. What is the residual? Residual is the condition on the right hand side, the known condition on the right hand side, which is U1 prime evaluated at 1 minus alpha must be equal to 0. That is, U1 prime must be equal to alpha. But I have indicated it in such a way that that residual is a function of eta, because different guesses that I make for eta will give me different residuals. And there is only one value of eta that will make the residual equal to 0 that I need to find out. So what have I achieved now? I have made this into a problem of two equations in two unknowns. Two equations are the residuals of the boundary on the right side, R1 and R2. Okay, so that is essentially the difference between the left hand side and right hand side. Okay, and I want to drive those residuals equal to 0. So I have two equations, two conditions, and I have two variables, eta 1 and eta 2. So I can apply the Newton method on that, right? Okay, so I have the vector, new vector that I have defined, vector function, okay, R1, R2, which is a function of eta. So the Newton method is quite straightforward. Okay, So I make a guess for the vector eta at the current iteration level p, and if I can find the correction delta to that, I get the next value, next guess. Okay, and how do I get the correction? I get the correction from the linearized version of the problem. R1 and R2 are nonlinear, pretty complicated functions. They are implicit functions because we don't know. There is no analytical form for the function, so I cannot just go and take the derivative of R1 with respect to eta 1. Okay, let's look at this. So this is the Jacobian, and this is the correction, and that is the residual. So when the residual is 0, the correction must be 0 if J is non-singular, right? So J is the Jacobian, which contains these 4 partial derivatives that you see here. Okay, so what do these partial derivatives contain? What does the Jacobian contain? The Jacobian contains information about, if I make a small perturbation in one of the unknowns, how much does the function change? Okay, that is what dr1 d eta 1 is, the partial variation in the residual 1 when I make a change in eta 1. Okay, and the same thing for dr1 with respect to the eta 2. But I'm not going to be able to calculate this because I don't know an analytical expression for r. In order to get that, I need to go through the whole integration process from the left side to the right hand side, and only then I can pick the numbers from the right hand side. Okay, so is this clear? How we have converted the problem into a problem of solving 2 nonlinear algebraic equations in an implicit fashion. So one trivial method would be to say I'm going to do a numerical evaluation of this Jacobian. What does that mean? I'm going to perturb only eta 1. Okay, so I make a guess for eta 1, for example 1, 1. Eta 1 is 1, eta 2 is 1. And I shoot. I go to the right side, and now from the right side I have these values u1 prime and u2 prime. I plug in there, and I have residual 1 and residual 2. They're not going to be 0 because my guesses are arbitrary, right? The next thing so that is one shooting. Okay. The next time I'm going to do is go back and solve the same problem one more time, but with eta 1 as equal to 1 plus 0.05, and eta 2 is still the same 1. Okay, so I perturb only eta 1, but when I perturb only eta 1, will it affect both R1 and R2? Answer is yes, because these are coupled equations, right? So even when I change only eta 1, there will be a change in R1, delta R1 and delta R2. So I can say dr d eta 1 is approximately equal to the observed change in R1 through this integration process divided by the imposed change in eta 1. So that's an estimate of the partial derivative. So if you make delta eta small enough, you'll get a fairly good estimate of what the derivative is. Okay. So in order to get this Jacobian, 2 by 2 Jacobian, how many shootings do I have to do? 3, right? First time, assuming one value of eta 1, eta 2. The second time, perturbing only eta 1. And that will give me both dr1 with respect to eta 1 and dr2 with respect to eta 1. That is the first column. It will give me the first column. Then I shoot a third time, this time keeping eta 1 constant, but perturbing eta 2. Okay. Then I will get the second column. And once I get J, I invert J, I can calculate delta, I put it in there, and I repeat the process. Because it's a nonlinear equation, you will not get the solution in one iteration, but you need to do several iterations. And each iteration means you need to make three shootings. Okay. Any questions? Right? How do we do it analytically? And that's a real nice contribution from these guys. This was done by Lavicek and Marek in a paper, and then they put it in one of their own book. I have given the reference. I think it's Kubitschek and Lavicek, numerical solution of nonlinear boundary value problems with applications. They have a lot of applications with chemical reaction engineering in there, I think. So this looks like pretty messy set of equations. The idea is not very difficult. Okay. The question is, how do I evaluate that Jacobian? That is the 4 derivatives, dr1 with d eta 1, dr1 with d eta 2, etc. analytically, okay, without doing a perturbation. Let me so ask you this question. Do you understand what is happening in the first equation? we are treating u1 and u2 as functions of eta 1 and eta 2. So we make a guess for eta 1, it's going to determine what the solution is. If we change eta 1, the solution will change. So we are saying that it is a continuous function of eta 1, so I can take the derivative of u1 with respect to eta 1. Okay? So this is the original equation that is given, except I'm taking the derivative with respect to the vector eta. Okay? So that gives me these 4 equations. Okay, the first equation is derivative of the first original equation that was given with respect to eta 1. And this one is the same equation with respect to the second equation. Okay, so this is the first equation with respect to eta 1. This is the second equation with respect to eta 1. And if you notice carefully, the first term, what have I done? I guess we need to see both equations. So this is the original equation. So I'm taking the derivative of this equation with respect to eta 1, and then this equation with respect to eta 1. Then I go back and take its derivative with respect to eta 2. But I have switched the order of differentiation, right? So I've taken the derivative of this expression with respect to eta 1, but pushed it inside. I can do that if u1 is a continuous function of x1 and x2 and eta 1 and eta 2. So I'm assuming the continuity. Okay? So that's why I get inside this du1 d eta 1, du1 d eta 2, etc. Then I go to this function and I realize that this is a known function. F1 is a known function, but it is a function of u1. So when I'm taking the derivative of that with respect to eta, I have to take the derivative of u1 with respect to x1 and then x1 with respect to eta. Okay? Basically, I apply the chain rule on that one. Okay? So if you go back and look at that equation. Sorry, df1 with respect to du1, because f1 is a known function of u1, but u1 is a function of eta 1. Okay, so the chain rule says that it is df1 with respect to du1 and then du1 with respect to d eta 1. Similarly, f1 is a function of u2, but u2 is a function of eta 1, and this is the derivative with respect to eta 1 the first time. That is equal to 0. Okay, but I also do one thing. What do? I take the given boundary conditions and I take their derivative also. So du1 prime d eta 1 evaluated at 0 equal to 0. Okay, and du1 prime d eta 1 evaluated at 1 is equal to 0. I'm treating u1 and u2 as continuous functions of eta 1 and eta 2. Okay, that's the basic idea. Then I do the same thing for u2, and then u1 again, this time with respect to eta 2, and u2 then with respect to eta 2. Okay, so these are with respect to eta 1, and these are with respect to eta 2. Okay, that's not a very conceptually difficult thing to understand, but if you're going to implement it in programming, you need to take all these partial derivatives. And you're going to treat all these partial derivatives of u1 with respect to eta 1, u1 with respect to eta 2 as unknowns. Okay, so all these are going to be treated as unknowns. So I'm going to introduce, so I'm extending the system. This is the same idea for a different purpose. I'm extending the system of equations so that I can get those 4 partial derivatives. That's my goal. Ultimate goal is to get those partial derivatives. So I have extended the 2 equations into 6 equations. Okay, treating the additional variables as I'm identified here. Okay, so du1 with respect to d eta 1, I'm indicating by a new symbol, pu1 comma 1. That's a new variable I have introduced. It simply says that it is the partial derivative of u1 with respect to eta 1. So the second subscript indicates what I'm taking the derivative with. Okay, and the first subscript indicates which variable it is, u1. Okay, so I have 4 additional equations. I have introduced 4 additional variables. Okay. So in terms of those 4 variables, all I'm doing is substituting. If you see, for example, du1 d eta 1 that appears here, that is the same as pu1 1. Okay, and if you take here du1 d eta 1, that is pu11. Take du2 d eta 1, which is equal to pu21. Okay, so I have now 6 equations in 6 unknowns, but they are all second order equations. Okay, so I can convert them into a set of 12 first order equations, but I need 12 initial conditions from which I should shoot. Okay, any questions? How do I get the 12 initial? I ordered the 6 equations here, creating a new extended vector x, and so the unknown variables are u1, u2, pu11, pu21, pu12, pu22. Okay, these are the 6 unknowns and their first derivative. So essentially there will be 12 unknowns when I convert these 6 ordinary differential equations into a system of 12 first order equations. Okay, and I need to now come up with 12 conditions on the left boundary without making a guess. If I have to make a guess again, I haven't solved anything, right? Because originally I had to make two guesses, right? And that's what I'm trying to develop, a method where I don't have to make any guess. So have I achieved that? And that's, if I can achieve that, then I have effectively built a method for, one shooting. Instead of doing 3 shootings, in 1 shooting I can get all the 4 components more rigorously without the perturbation. Okay, the only error in that would be the error in the discretization error that you will see. So I've also kept track of all the boundary conditions, okay, on both sides. These come from the original boundary condition that was given to us. They're all in terms of primes. So p prime is the derivative of p with respect to x. Okay. So where do we get the 12 unknowns? Well, you can count here 1, 2, 3, 4. Right? There are 4 on the left boundary, and there are 2 that are originally given also on the left boundary for u1 prime and u2 prime. Okay, where do we get the remaining ones? So let's count this carefully. Okay, so I'm going to first highlight the ones that are given, and then tell you how we get the remaining one. So u1 prime is given to us already. u2 prime is given to us. Okay, so from that we take its derivative with respect to eta 1, with respect to eta 2. So this entire row is coming from the given equation by taking its derivative. Okay, they're all on the left boundary. So that gives me 6. Now the others, okay, I made an assumption about what the values are. So this is assumed. So u1 is assumed to be eta 1 and u2 is assumed to be eta 2. So I give an initial guess for eta 1 and eta 2, so I know what they are. Okay. Now I can go back to that and take its derivative with respect to eta 1 and eta 2. So if I take the derivative of u1 with respect to eta 1, what do I get? It's 1. If I take the derivative of u1 with respect to eta 2, it's 0 because it doesn't depend on eta 2. That's how I get this term. Okay. And then I go to u2. Derivative of u2 with respect to eta 1 is 0. And u2 with respect to eta 2 is 1. Okay, so I made 2 guesses for eta 1 and eta 2, and now I have all the 12 conditions. So I have to convert them still, the 6 equations to 12 equations, and then integrate, and I will get all these 6 variables on the other side. Okay, as I integrate from left side to the right side, I will get u1, u2, pu11, pu12, pu21, pu22. All of them I will get on the other side. Okay. But what do I need? I don't need all of them. I need only dr1 with respect to d eta 1. What is dr1 with respect to d eta 1? What is r1? R1 is the residual, right? Which is u1 prime minus alpha equal to 0. Okay. So when I take the derivative of r1 with respect to eta 1, it's going to be du1 d eta 1 minus derivative of alpha with respect to eta 1, but alpha is a given constant, right? So all I get is du1 prime with d eta 1. But what is that? That is pu11 at the other boundary. So after I integrate all these 6 variables with 6 equations, I just pluck these 4 numbers. What is PU11 prime at the right side? Okay, and what is PU12 prime, and PU21 prime, and PU22 prime? Okay, those are obtained as solutions to those the initial value problem. Okay, 6 equations in 6 nodes, and 12 conditions that are given here. You integrate, and when you go to the right hand side, you are going to get all the values, like particularly the values that are on this line, but evaluated at x equal to 1. Right? As you're integrating, you're going to get all the values that evaluated at equal to 1. And those are the only values that I need here to construct that.
Just so I'm understanding this, you need the 12 equations and 12 boundary conditions.
Initial conditions.
So initial conditions. So you can shoot.
Yeah.
And then you only need 4 of them so you can iterate again.
Right.
Okay.
Exactly.
So you can advance to the next shot.
Yeah.
Okay.
That's the price you pay, right? Even in the extended systems for limit points and stuff, we extended our equation and we calculate the null eigenvector. We really don't have any use for it.
Right.
All we want to do is impose the eigenvalue equal to 0.
Right.
But that's the only mechanism that allows us to do that. So the same way, there are this set of variables at every value of x we calculate, but we don't need it. What we need are only these 4 numbers, and also not everywhere, only at the end. Okay? So at the other end. So you take that and plug it in here. So you have j, you invert it, and then you can get your correction vector delta and put that in a cycle. So in one shooting, you get all the 4 values, and more accurately. Because the other shooting numerical evaluation, you need to make a judgment of what delta eta should be. But here, you get d r1 d eta 1 directly from that derivative. And they go on to look at limit points and stuff beyond that, okay, how to implement that. But I thought this was a very clever way of building yet another extended system to be able to construct the Jacobian. But of course, because it is nonlinear, one shooting won't do. You're going to get a correction, and you need to monitor that the correction goes to 0. Then only you have conversion.
Will you still get you'll get quadratic convergence with the Newton method?
Yeah.
But how does that translate to convergence for the entire shooting method?
The question is, for the benefit of those in Abu Dhabi or online, the Newton method is guaranteed to converge quadratically, but how does that translate when you're using it with the shooting method, right? That's a good question. I don't know whether any error analysis has been done on these kinds of methods to give you a definitive answer. Like Newton method, there are proofs that it converges quadratically, and we see that. The only source of error that we introduced in calculating the Jacobian, that is those parts of the algorithms that are related to Newton method, would be the truncation error in shooting from the left side to right side. Okay, so that will introduce an error in estimate of all these derivatives. And does that degrade the quadratic convergence? I don't know the answer to that. It's a good question. I would suspect that if you use a fairly accurate method with a truncation error of h to the power 4 or something like that, and with reasonably good size, you'll probably still get close to quadratic convergence, I would think. Yeah. I have not actually implemented that to see whether that's one. I cannot prove, I'm not a mathematician, but I can test it out, take it for a test drive and see whether it really gives you quadratic convergence or not. Okay, any other questions? It's not a very difficult idea, but it's a very neat idea on how to implement. Put together all the ideas that we have seen: Newton method, shooting method, ODE integrator, everything put together. Okay, so I've been struggling on how to take this course from this point on, because there is still a lot to be done in the agenda, in the outline. We have done a lot, and we still, I wanted to touch upon many areas. So what I've decided is I will focus on the finite difference methods and cover that, expose you to all the types of approximations, but in going from ODE to PDE, because we haven't touched about PDE at all. I don't want that to be in the last two lectures. And so we'll talk about classification of PDEs and finite difference methods for PDEs, some of the ideas. They are fairly easy extension, but the classification may be a bit difficult. And then we'll go back to functional approximations, that branch. We'll, starting with ODEs, boundary value problems, collocation methods, and then see how they are applied to partial differential equations. But we are not certainly going to have time to look at finite element and finite volume methods. I think we are really running out of time. So, classification of PDEs. How many of you have heard of these classifications? 1, 2, 3. Okay. How is the exposure at guys? So, have you guys heard of parabolic, elliptic, hyperbolic classification of PDEs? Heard about it? That's okay. We will see a little bit more detail, more than just hearing about it. How do you actually, okay. So, oops, nothing more coming. Okay. So the terminology comes from conic sections, from quadratic equations. Okay, so just a brief review from Wikipedia, essentially. Okay, so if you have a general quadratic equation written by this, it's just an algebraic equation. Okay, we're not talking about PDEs yet. Algebraic equation. It's a quadratic equation: ax squared plus bxy plus cy squared plus dx plus ey plus f equal to 0. We classify them as belonging to quadratic curves as either an ellipse, representing an ellipse, or a parabola, or a hyperbola. Okay, based on this quantity, b squared minus 4ac. These are the coefficients that appear in here, a, b, and c. So in general, these really do not matter. They do not determine the character of the quadratic. They are all linear terms. So it is the quadratic terms and the coefficients of those that determine whether that curve is going to be an ellipse or a parabola or a hyperbola. Okay, and if it is an ellipse, you know that the canonical form of that can be put by suitable transformation. You can actually get rid of this x, y, and other terms and write it as simply this. So this is a transformed coordinate x, y to psi from x comma y. You translate and find a coordinate transformation to a new coordinate psi 1 and psi 2. Okay, and in that new coordinate, the same equation can be expressed in terms of this by simply getting rid of these terms. Does anybody remember what kind of coordinate transformation that would be? You will see it later on. The eigenvalues and the eigenvectors of a certain matrix will give you the coordinate transformation. The same thing applies for differential equations. If you're given a partial differential equations in a Cartesian frame, if you can find its natural coordinate system, eigenvectors provide that natural coordinate system, you can put it in this form. Or you can translate it. This simply says psi 1 minus h, it should be psi 2 here, sorry about that, minus k squared. So that says instead of the ellipse being at the center, if you translate it, a distance of h and a distance of k. And of course, when you expand this one, what are you going to get? You're going to get the first terms, okay? In addition to the x squared term, you will get the x term and you will get the y term. And that's what this one is, okay? So this is in an arbitrary location, orientation, etc., whereas this is in terms of its natural coordinates, eigenvalues and eigenvectors. Now, they are all these curves, whether it's a parabola or ellipse or hyperbola, are treated as, this is a nice picture I saw last night from Wikipedia, of a conic section. Okay, So it nicely illustrates what happens. If I have a cone and I can cut the cone in a number of planes. For example, if I cut with this plane that is kind of parallel to the base, then I'll get a circle. Okay? But if I tilt it to the base, then I get a ellipse. Okay? So, and if I tilt it in such a way that it is parallel to one of these surfaces, okay, that's a very special case, then I get a parabola. Okay? But any other angle that I tilt, not just the one that is parallel to it, I'll get a hyperbola. Okay? And b squared minus 4ac, that condition basically tells you which one of these orientations of the plane that I cut that would result in the intersection of the plane with the cone as a surface, as an equation, as a curve. Okay? So for a hyperbola, it is I1 square over a square minus I2 square over b square equal to 1. Now let's look at the quadratic terms only from that equation. So on that equation we had ax square plus bxy plus cy square plus dx plus ey, etc. So if I take only the quadratic term, I can write the same equation as in vector matrix form. Okay? So I arrange the coefficients a, b, c into this form, a, b and b, c. And then I multiply, pre-multiplied by a vector x comma y, coordinate points, and post-multiplied by the same position vector x comma y. Okay. And I set that equal to 0, for example. So if I do that multiplication, what will I get? I'll get the quadratic part. Question? Okay. So you will get the first part of those equations, ax squared plus bxy plus cy squared plus 2bxy probably. Okay. And lambda 1 and lambda 2 are the eigenvalues of this matrix A that you see here. Okay. So another classification for this is to simply say that if any lambda is 0, so it will have two eigenvalues in this case. Okay. The reason that this is good is it allows us to generalize to multidimensional partial differential equations, system of partial differential equations, etc. Okay. Still, its own classification is only a guide. There are problems where you cannot classify them. We will see why that is so. Okay. But only that condition, b square minus 4ac greater than equal to less than, is good only for that quadratic equation in 2 space dimensions. How do I do it if I have 3 space dimensions? Okay. This formulation will allow you to generalize that. So if any lambda is 0, then the equation is parabolic. Okay. If all the lambdas have the same sign, then it is elliptic equation. If any one of them has opposite sign, then we call that as hyperbola or hyperbolic. Okay. Now, in this framework, it's very easy to generalize the quadratic equation into 3 space dimensions. Now I have ax squared plus cy squared plus fz squared plus all the first order terms. Sorry, they are still second order terms. Because the first order terms don't make any impact, we just neglected them. Okay? So that can be written in this form. Okay? The coefficients can be written as a, b, d, b, c, e, d, e, f. All the coefficients, okay, of the quadratic terms. Once again, the same classification. Oops. Okay, so the eigenvalue problem, A is the matrix that you see here. Okay, this matrix is that. And the eigenvalue problem is A multiplied by Vi equals lambda times Vi. And that is a symmetric matrix. So what do you know? Let me prepare you for your final exam. What do you know about the eigenvalues and eigenvectors of a symmetric matrix? They're all real. They're all orthogonal, right? If it's not symmetric, then it is bi-orthogonal. So you can find the left eigenvector and right eigenvector sharing the same eigenvalues. And so all you need to calculate the left and right eigenvector is simply transport that matrix. Transpose a matrix and pass it to the EIG routine. It will give you the left and the right eigenvector. But if it is symmetric, when you transpose it, you're going to get the same value, right? So there is only one set of eigenvectors, and they are orthogonal. In this case, orthonormal. Okay. So this is the one that says it's orthogonal, and that's a normalizing condition. So if I then make a relationship between my Cartesian frames x, y, z and my new transformed coordinates psi1, psi2, psi3, or the coordinate points in the new coordinate. What is my new coordinate? v1, v2, v3. Those provide as the basis vectors. So I'm representing the same point in terms of a new basis vector, taking the eigenvector as the basis vector. Okay. So when I subject, that is, if wherever I have x, y, z, I replace it by psi1, v1 plus psi2, v2 plus psi3, v3. Okay. And what do I get? Well, on the left side I get psi1, v1 transpose plus psi2, v2 transpose. That is this term you see here. Okay. So that has been replaced by this term. And then I have A as it is. And then this term is the right side. I guess I should have it as 1A. Okay, because I have 1A. It's 1. Okay. Now what do I get? I have to multiply term by term. So V1 transpose A V1. A V1 is lambda V1. Right? So I substitute that with lambda times. But V1 transpose V1 is 1 because it's a orthonormal basis sector. So all I will get is lambda 1 times psi 1 squared. And when I take V1 with V2, what do I get? 0, because they are perpendicular to each other. So this shows you how the coordinate transformation is done from a Cartesian frame to its natural basis in terms of the eigenvectors. Okay? And what you get is this equation. Once again, if all the eigenvalues are the same sign, then that's going to be an elliptic problem. It's an ellipse in a three-dimensional, ellipsoid, I should say, in a three-dimensional phase. Right? So if any of them change sign, then it is hyperbolic. If any one of them is 0, it represents a parabola. Okay? So this is from a quadratic curve from in 2 space dimension and 3 space dimension, and that provides us the basis for defining the classifying the partial differential equations. Okay, so the same concepts. Okay, now we are applying it to differential equations. So uxx stands for the partial derivative, second partial derivative of u with respect to x. Similarly, uxy would be the derivative of x with respect u with respect to x and y. So once again, these terms do not contribute. It's only the second derivative term. Okay, the first 3 terms that contribute to the classification. And it's the same classification that you will see in a very first partial differential equation course without really telling you why it is. And the underlying reasoning is the eigenvalues, the sign of the eigenvalues of a corresponding matrix. But it's simply given as b squared minus 4ac less than 0, it's elliptic, equal to 0, it's parabolic, greater than 0, it's hyperbolic. Okay, so that's just a classification. And the methods that we use to solve these partial differential equations depends to some extent on what type of classification it is. We have one class of method for parabolic and hyperbolic equations. They are called evolving equations, evolution equations. Whereas elliptic is typically an equilibrium type of a problem. There is no element of time or element of marching in space in one of the directions. Okay? So examples of this would be a heat diffusion equation. So if you are given this equation, what you need to do is map and see what the coefficients are so that you can classify it. For example, the first derivative you know doesn't contribute. Right? The second derivative, if I take x to be associated with this, then alpha is a. But there is no second derivative term with respect to t. Okay? So b is 0 and c is 0. Okay? So if you plug that into b squared minus 4ac, well, b is 0 and c is 0, so that is equal to 0. So that's a parabolic equation. That's an evolution equation. Okay, so you have u evolving in space and in time. Okay, in space it's a second order equation, so you will need some sort of a boundary condition. So if this is x, maybe x may be going from 0 to 1, and this is the time axis. Okay. So in that domain, the solution is going to evolve for each value of x along this time you will need the solution. So the solution is going to be u as a function of x and t. So we need to discretize that. Okay, how do we discretize that using finite difference is what we are going to see. Okay, any questions on that? So here is an equation which comes from, I guess, compressible flow. So it is 1 minus m infinity square times d square phi dx square plus d square phi dy square equals 1. Okay. So here we have two terms that are second order, in x and in y. Okay. So I need to take, for example, x so associated with a. So the coefficient a is 1 minus m infinity square. M is a constant. The physical interpretation for that turns out to be that it's a Mach number, okay, for compressible flow. And there is no cross derivative term xy, but there is a term that goes with d squared dy squared. Okay, that coefficient is 1. Okay, so you substitute that in b squared minus 4ac, you'll find that d is equal to 0, so it is minus 4 times a is 1 minus m infinity squared and c is 1. So this is what the number turns out to be. So this equation changes its character, right? If m is less than 1, we call it subsonic, okay, and it is elliptic, okay. So elliptic problem, or as I said, equilibrium problem. So if you know what the values are on the boundary, then you can predict what is inside. Okay, so a geometry for this may be some sort of a closed region in an xy space. So if I know what the values are on the boundary, that is the boundary condition. I must specify what the boundary condition is. Then I want to satisfy this differential equation so that I find phi in the entire domain that is of interest. Now, if m turns out to be greater than 1, then I have that as greater than 0. M is greater than 1, that makes it negative, and that negative, that makes it positive. So that's an error. Okay, so that makes it supersonic. So what do you know about supersonic flows? We are not mechanical engineers, I guess. Any mechanical engineers here? Petroleum engineers may know about Berkeley-Leverett equation. Have you heard of that? No? You're not quite petroleum engineers. Okay. Geotechnical. So you get shock waves, okay? The supersonic transport planes, the Concorde, for example, is a good example of that. As you cross the Mach number of 1, the speed of the sound, you'll get a big sonic boom. Another example is the water hammer problem. Okay, you can go back home and let the hot water tap run and then just shut it. You will hear a big bang in that. So that's a pressure wave that is propagating. So typically, hyperbolic equations have that kind of a character, that they can sustain as solutions discontinuities, and these discontinuities can propagate, and these are called shock waves, simple waves and shock waves. The theory behind that is fairly well developed, and in fact, chromatographic separation, for example, is also governed by hyperbolic equations. So the next example is, we have seen an equation of this form without the time derivative. If you remember, that's a convective diffusion equation. So here you have a convective term, and here you have a diffusive term, and you have a transient term. So to make it into a PDE, we are looking at the transient effect of convection and diffusion. What do you notice about that problem? It's a partial differential equation. It's a scalar equation. U is the unknown. U is a function of x and t. RE is the parameter. Can you classify that as elliptic, parabolic, or hyperbolic? In order to be able to do that, what you need is, you need to figure out what the coefficients are. Okay, one of the coefficients is minus 1 over RE, it's a constant. But the other coefficient is U itself, the solution itself. Okay, so if you associate, but this is a first order term, so maybe you can still classify it as a it will end up as a parabolic equation. Okay? But there are situations where you have a nonlinear term appearing as a coefficient. So this classification is no good for such nonlinear problems. And the classic example is that Navier-Stokes equation itself. Okay? If you ask the question, what is the Navier-Stokes equation? Is it elliptic, parabolic, or hyperbolic? It is all, depending on where you operate. If the Reynolds number is very small, and if you have no transient fx, then it's essentially an elliptic problem. Okay? But if the Reynolds number is high, that is a convective term, that is this term is high, then it can behave like a hyperbolic equation or a parabolic equation. Waves, for example, are all hyperbolic phenomena. Okay? So it's very difficult. So this classification is only good for us to kind of launch in the right direction for developing numerical algorithms. What have we been doing all this time? We developed methods for linear systems and apply to nonlinear systems locally by linearizing it, right? So in that sense, the linear classification for the linear PDEs helps us. Okay, this class of methods works for elliptic problem. This nonlinear problem behaves in an elliptic manner, so I can apply that particular method. Okay. But the beauty of these CFD solvers is that they try to capture all the behavior in their numerics. Okay. In certain regions, if it is hyperbolic, the numerics should capture the hyperbolic nature of it. And in the process, we come across these numerical stabilities that we need to appreciate. We already talked about, for ordinary differential equation, what a stability is. We've talked about algebraic equations and fixed point iteration when an iteration is unstable, diverges. And similar issues occur with partial differential equations also. At certain times, the discretization that we have will remain stable, numerically stable, and other times it will be numerically unstable even though the physical system is stable. So we need to develop an appreciation for those concepts. Any questions? So this is extending that definition, again going back to the linear problem, in 3 space dimensions. Okay, so you have a PDE that is a function of x, y, and z. Okay, and these are all the quadratic terms. So we can assemble that in the same way as we did for quadratic curves, but except now we have partial derivatives instead of the position vector. So the partial derivatives are operating on that variable u. So these two equations are exactly the same. Once you do the coordinate transformation, after you find the eigenvalues and eigenvectors of this 3×3 matrix, you can reduce this equation into this form, into its canonical form. Okay, in the coordinate psi1, psi2, psi3, and the classification will be exactly the same. If any lambda is 0, then we end up with a parabolic equation. If they all have the same sign, it is elliptic. And if any of them have opposite sign, the partial differential equation is hyperbolic. So this gives us a mechanism for generalizing the classifications into any number of space variables. Okay? And also to a system of equations, because you need to find the corresponding matrix of the system of equations and apply the same rule. So that b squared minus 4ac has been recast into conditions on the eigenvalues. Okay? And that carries through for a whole variety of problems. Okay, so we have some appreciation of what the classification of partial differential equations are, something about the physical response of each one of these 3 systems. What you need to take away is, if you have an elliptic problem, it is an equilibrium problem typically, and only the boundary values determine what happens inside. Those are often very well-behaved systems. When you have hyperbolic or parabolic, they are typically evolutionary systems, evolving in time or in space. There is time we will talk about spatial evolution. The Prandtl-Boundary theory is a good example of a parabolic equation in space, not in time. It's a steady state problem, but things evolve in space. And first I'm going to review finite difference approximation. So this table is the one that we need to replace every derivative in a partial differential equation with a corresponding finite difference approximations. It could be time, it could be more than one space dimension, but the basic idea is if I have a first derivative, I can approximate it by any one of these approximations. Okay? And the most common one would be this central difference in the center. and forward and backward differences at the edges. And similarly for the second derivative, it will be plus 1 I minus 1, central difference in the okay. But for first derivative in time, we will find that we will use these, okay, forward or backward difference approximations. And they are not very difficult, so I think we should be able to finish it hopefully today. Okay. So I'm going to take the convective diffusion equation. Just a series of ideas that help us formulate the problem in different ways. Okay? So here is the equation. It's a parabolic equation, as we saw. It's an evolutionary equation. And it's a second order equation, so I need two conditions at x equal to 0 and x equal to 1. So one can think of this as a mixed problem, boundary value in x, but initial value in time. That is elliptic in x, but parabolic in t. If you want to think about it, that's fine. Okay? Question? Okay. So, and we have first order equation in time, so I need an initial condition. Okay? And what I'm going to do is set up a grid in space and in time. So this is the space direction x, and that is my time domain t. Okay? So in the so-called method of lines, what I'm going to do is I'm going to reduce this partial differential equation to a system of ordinary differential equations. So I'm going to do only spatial discretization that you see here. Okay? So the variable u as a continuous function of x and t is discretized, is approximated by saying u is evaluated at xi, only at those nodal points. I won't have an idea of x u at any other x values. Okay, that's a discretization process. But I'm still treating it as a continuous function of t. Okay, so instead of u as a continuous function of x and t, I'm going to indicate with a subscript I. ui, so u1, u2, u3, etc. So those are the discrete locations in space, but it is treated as a continuous function in time. That's the method of lines. And what does it do? It simply draws lines in the time domain. Okay, and for each line, I get one ordinary differential equation. They're all coupled, and I just integrate in time using ODE 4.5, RK 4.5, RK 1.5, whatever it is. Okay, so you need to now compare term by term. Okay, so let's take this left term, du dt. So I'm leaving it simply as dui dt. That means I'm taking such certain point I, and along that line I'm going to evaluate the partial differential equation. Okay, so if u appears there, it simply becomes a total derivative dui dt, because ui is only a function of time. Okay, and so this is going to give me a new function which I need to plug into ODE 4.5. Okay, so we need to find n equations in n unknowns and the n functions. On the right hand side, I have okay, so I have this term d square u d square. That I replace by the central difference approximation at I. Okay, so it's going to be ui plus 1 minus 2 plus ui minus 1 over delta x squared or h squared. This has a truncation error of order h squared. But I can do that for every value of I, for 1, 2, 3, etc. Okay, that's what I do. So I end up with n equations. Okay, n is a choice that I make because I want to know what the truncation error is. Okay. So I've converted that PDE into a set of ODEs without separation of variables. If you do it analytically, you will do the separation of variables, you'll convert it into ODEs, and you will still solve them. Okay, using the similar ideas from Fourier series, etc. But here, I've converted them into a system of ODEs. But I say that they are coupled. What does that mean? If I'm calculating the value for every time, for example, I do the discretization in time. Okay. So this is T1, T2, etc. Okay. So I need to, in order to calculate this, I need the value not only of the previous time step, but also the other variables. right? In order to calculate that function fi, I'm going to use ODE 45, so I'm going to project from this time to that time step using delta t. Okay, and I can use RK45, but what happens on the three values below is going to affect what I predict for the next time step. Okay, and that's true for every one of them. So if you ask the question, how does the boundary condition get propagated into this? How would I set up an algorithm? How would I write in MATLAB, for example? All I need to do is write a function which evaluates all these. Suppose I pick n equal to 20. Okay, so I have delta x equal to 0.05. Okay, so I need to write a function that calculates all these 20 functions and returns it to RK45. RK45 will march for each one of those 20 values, construct a solution along those lines. Okay, how does the boundary condition enter? How does the initial condition enter into this? So this is an ordinary differential equation. So I need to provide a set of initial conditions t equal to 0. Where would that come from? It comes from that. Okay. So in this particular problem, it is all 0. Initially, think of this as a rod that is being heated, for example. Initially, it is at 0 temperature. At time t equal to 0, you bring the left one to a hot temperature. The right one is at a cold temperature. Right? And then it's going to heat up. What would be the final temperature? Do you remember from heat transfer, from transfer phenomena we did? When it reaches a steady state, what happens to the left-hand side? 0. So you get a second order differential equation. You integrate it twice, you will get a straight line. Okay. So the temperature profile is going to first go through in a nonlinear fashion, something like this maybe, as time increases, but eventually it will become a linear profile. Okay. And that's what this integration should give you. At every instant of time, what is the temperature profile across that length? So the initial condition comes from this. And where does the boundary condition enter? When you evaluate the first function f1 for this point, for u1, you will have u0, which is from the left boundary. Similarly, when you evaluate it for the last function, that will involve un plus 1. Okay. So suppose I had given this, instead of saying 0, I say this is sine phi t. What would change in the problem? How would you expect the solution to look like over a long time? It will just be an oscillation because you're forcing the oscillation from the right side. Okay. So how do you implement that in your RK45? No different, because when you are evaluating, for example, F20, you need F21. But you're going to use the current time level, plug it in there in calculating the F21. That's all it is. So you are forcing. What would you call that? Autonomous or non-autonomous? For the ODE? Non-autonomous system, right? Because time appears explicitly in that case when you have that function. Even if it appears in only one, it's still non-autonomous because they're all coupled. Okay. So you get an idea of how to handle a parabolic partial differential equation. What would change if I had a different term plus 5 times du dt, du dx of partial derivative? What would change? The idea is the same, right? Now you're going to have a second additional term here that will be central difference approximation for the first derivative. Okay. What would change if I have 2 equations instead of 1 equation? Nothing changes. It's the same idea, right? So it's not really, finite difference method is not difficult, but what we need to understand is the stabilities of these algorithms and the consistency of these algorithms. So those are new concepts that we need to talk about. Hopefully by next lecture we will get there. Okay. Any questions? Yeah.
Just to kind of bring it all together, when we're at the boundary, for instance, we can't use the simple difference of that.
Good point. Actually, I forgot. I'm glad that you brought it up. When you are at the boundary, do you need to use any central difference or forward difference or backward difference? If you have, a Dirichlet boundary condition like this, a known value, then you don't need that. Okay, all you need to do is evaluate whatever the function is. The function can be a function of time, but similarly, initial condition I said is 0, but it need not be 0. Here I could have a function initially that is, for example, the same heated rod problem, it's linear temperature, and I'm shutting off the temperature at the left. I'm cooling it, right? So the two boundary conditions could be homogeneous, but the initial condition is it's a linear function, so it could be a function of x. Okay, as long as you have I hope I'm getting the gist of your question, right? As long as it's a Dirichlet problem, Dirichlet boundary condition, you don't need to worry about what approximation do I use at the boundaries, because there is no approximation to be made. But if I have again, let's take this fin problem. Okay, so I have u equal to 1. Oops. Okay, so if this is a heated fin, okay, and this is x, and the equation for that becomes du dt equals alpha times d squared equal to x squared plus hp times u minus u naught or something like that. Okay. That is, the heat loss to the surrounding is captured by this term, okay, and that is the convection term, and that's a transient term. So the fin is initially cool, and then I heat it up. Okay, so there is a transient evolution. Now, in that case, you could have a boundary condition where the tip of the fin is insulated. Okay. Then what you will have is, on the right boundary, you might have a boundary condition du dx at x equal to 1 is 0. On the left boundary, you might have a condition that u is equal to 1. So Dirichlet condition on the left, but the Neumann condition on the right. Then I don't know what the temperature is at the right boundary. I know only its derivative. Then you have to worry about what do I do with that. Okay. So what would you do? You would try to find an approximation for the first derivative that is consistent with the approximation that you made for the pole. Okay, so that means you would go back to the table and say, what is a backward difference formula? Because I'm on the right boundary, I need a backward difference formula. So what is the backward difference formula that is for first derivative? Fourth, and that's a fourth one. I would use that. Okay, that will involve I minus 1, and I minus 2, the last 3 points. Or you can use the idea of using an extended fictitious point and getting rid of it. So using a central difference point, but you'll introduce n plus 2 and get rid of n plus 2. Okay, we have seen that also for boundary value problem. So in that sense, what I said, that there's really not a lot of new ideas in finite difference method, but just becoming comfortable on putting all these two together, no matter what the problem is that is thrown at you. Okay. Yeah.
Is the use of the method of lines advantageous over just discretizing the time term? Because you'll get a higher order?
You get, yeah, that's a good question. You get, the question was, I guess, is the use of method of lines advantageous compared to doing a discretization in time also? In fact, I have other methods that we're going to talk about where you discretize the time explicitly or implicitly. The main advantage is that you get to use the powerful initial value problem algorithms of much higher order in time. But you should keep in mind that if you are restricted to a certain approximation in space, delta x square and delta x is 0.05, there's no point in beating it to bush by saying that I'm going to use a very high order. Matching the order is very important. Matching not only the order, but also the order of delta t and delta x, so that the truncation errors remain of the same order. Okay, so that's why it's not really very popular, but some method historically it has been developed. And I'm going to present a number of methods that are developed and look at, essentially try to understand the thought process that evolved in developing these algorithms. Why people started worrying about stability and consistency, things like that. So, if this is a situation where boundary condition is a function of time, it's still a Dirichlet problem. All you need to do is, when you need the value for the very last point as you are integrating in time, you take it from there at that particular time. that will force the solution to oscillate. Now, the second method is called the forward time and central space, and that's your question. The question is, can we replace the left-hand side with also a finite difference approximation, and if so, what are the choices that are available? One is called the forward time, and still we are using the central space, which has a truncation error of order delta x squared, but it is forward in time, so just first order forward in time. Okay, and so we have discretized both variables, so x becomes xi and t becomes tn, and typically you will find it in books denoted as u subscript I superscript n, subscript indicating the time discretization, I indicating the spatial discretization. So this is ui n plus 1 minus ui n. So just like in partial derivative, this is actually du dt. The meaning of that is I'm taking the derivative with respect to t, keeping x constant, right? And similarly, this is d square u dx square, taking the partial derivative with respect to x, keeping t constant. So when I keep x constant, that index will remain the same in every term. Okay. Similarly, on the right hand side, t is constant, so n will be constant. So the derivative is only with respect to x. That means I minus 1, I plus 1. So the truncation error is of order delta x square and delta t. So it is important for us to pick a delta t that is of the same order as delta x square. What does that mean? If I pick delta x as 0.1, then the truncation error is of order 0.01. So your delta t should be of order 0.01. Otherwise, you're not matching the truncation error. Okay. Now that is called an explicit method. Why is it called an explicit method? So, how would you apply that method? So I rearrange that equation and I divide my time domain, okay, as two levels, for example, plus 1 and n. N plus 1, and this is nth level. So when n equal to 0, I'm at the base level, time equal to 0. I know all the values. So on this line, I know all the values from the initial condition. Okay, and I'm trying to predict what the values are at the next level. Now I don't have time as a continuous line, which is discretized. Okay, so I'm trying to calculate all those points at the next level. So if I'm calculating the value at this level, if I look at the formula, so on the left side, I have the level at n plus 1. But everything on the right hand side is at level n. And that's why we call it an explicit method, because they're all known. Okay? So this is known, and this is known. And those are the only values that appear. Ui at n, which is this value, and at n plus 1, which is this value, and n minus 1, okay, which is this value. So it's an explicit method, but it has this group alpha delta t over delta x squared. So the stability of this method is determined by group, and we're going to see how we determine that stability later on. Okay? So it's called an explicit method because everything on the right hand side is known, only one unknown on the left side. And all you need to do in MATLAB is just 3-4 lines of code, because you need to put a loop for I going from 1 to n, a finite loop, and another loop for n going from 0 to however long you want to integrate. You need to decide on a final time, okay? And that's what will give you the whole big array of numbers that you can then plot. So it is called an explicit method, but the question is it stable? And the answer turns out to be it is conditionally stable. As long as that number alpha delta t over delta x squared is less than half or something like that, it will produce bounded results. Otherwise, it will blow up, even though the original partial differential equation has stable solutions. So how can I make this method stable? We will study about von-Neumann stability analysis later on, once I cover all these class of methods. Okay? But we already know that from ordinary differential equations, if you go from explicit to implicit methods, it becomes stable. Okay? So the same idea. So we are going to make this implicit by saying that I'm going to consider a backward time central difference in space. So in time it is backward difference. What is that? How does it change? Okay, so if I have, often this is used in the form of these stencils to show how the points are related. Okay, so if I take in the explicit method, I took this kind of a stencil. So I predict this one by knowing what the three values are. Okay, and it is as if I have used this as my reference point in doing central difference in space and forward difference in time. Okay, so why can't I take a stencil that looks like this with this as the reference point? So I'm still using central difference in space, but I'm using backward difference in time. Okay, and it's the same formula, some indices change, that's all happens. Okay, so it is uin plus 1 minus uin. So you treat this as the n plus 1th level, and you treat this as the nth level. Okay, so n plus 1 minus n. That looks like makes it look like a backward difference. So it makes this as your reference point. Okay, on the right hand side you have everything evaluated at the n plus 1th level. Okay, all along the n plus 1th level, and I don't know any of them. Okay, that's a problem. Okay, so if I take, for example, along this, okay, so if this is time level n and time level n plus 1, I'm trying to calculate these values. Oops. Trying to calculate a value here, a value there. Of course, that value is on the boundary. I know that. Okay. And similarly, if I take a point here, this would be the stencil. So when I'm trying to, sorry. That would be my stencil. So the three central difference terms on the right side are all these three, and I don't know any of them, but I know the previous value n, which appears here. So this is known. Okay, so that is known, but this is unknown. Anything at n plus 1 level is unknown. So I need to move it to the right hand side. Okay, and sorry, anything that is unknown, I move to the left hand side, move this to the right hand side. Rearrange that equation. What do you think I will get? This is what I get. Okay. At the n plus 1 level, I have I minus 1, I, and I plus 1. The same equation, just rearranged. And beta is the coefficient, which is alpha delta t over delta x squared. I know that. Alpha is given in the problem, and delta t, delta x I choose. Okay, and this is the only one that is known on the right hand side. That's at the previous level. And n equal to 0, that's your initial condition. So what do I need to do? I need to solve at every time step a system of linear algebraic equations. What would be the structure of that matrix T? Tridiagonal. Okay. If you have Dirichlet boundary conditions on both sides, that will end up with a tridiagonal system. If you have a Neumann condition, and if you choose to use a 3-point backward, it will destroy the tridiagonal structure. So all these things carry forward. And the vector is basically the vector of unknowns, u1 to un, at each time step. Okay? So each time step requires you to put in more additional computational effort by inverting this matrix. But it turns out that this matrix is, for a linear problem, it is a constant matrix. So you need to invert it only once. And then it is just a matter of new right-hand side coming every time and doing a vector matrix multiplication. So efficiencies become very important when you're dealing with not this kind, but if you have 3 spatial dimensions and 4 equations. Okay, so to assemble that matrix itself will be a tremendous amount of task. It will be block tridiagonal structure, and so if it is constant, then you invert it once. If it's a nonlinear problem, then you need to evaluate that T matrix every time, because T will itself will depend on the solution. Okay, I guess we are almost out of time. So there are a few other simple methods, and then we will talk about this important idea of consistency and stability for partial differential equations. And then once we finish the finite difference, next week hopefully we'll start doing the collocation. Am I going fast? Remember, it's just kind of an exposure to ideas. Okay, I'm not expecting you to actually write a code on this one. All right. See you on next.